So today I am going to talk about supersymmetry in quantum mechanics, and I hope that all the students who are attending have taken first course in quantum mechanics and have studied one-dimensional harmonic oscillator, because my lecture essentially assumes that you have done that. Once you have done that, I am hopeful that many of you can understand. And if some of you have some questions or difficulty, at the end of the lecture, you can ask me some questions. And also, I have given my email address. So if please feel free to send me email about your questions and something. I will be happy to answer those questions. Okay, next, please. Okay. And my today's talk is mainly based on the lectures I gave in Latin American school in Mexico City in 2004. And you can see that in this archive, Math PH 0409-003. So those of you who don't follow all the steps here, you can always look back there and understand. Okay. So coming back to the topic, by supersymmetry is a symmetry between fermions and bosons. Now, if you just think for a minute, it is a highly unusual symmetry. Why? Because fermions and bosons have very different physical properties. As we all know, identical bosons condense, the so-called Bose-Einstein condensation. On the other hand, no two identical fermions can occupy the same state. However, remarkably, people have introduced symmetry between fermions and bosons. This was first introduced in high energy physics to describe unified description of all basic interactions, namely quarks and leptons and mediating particles. So now, as we all know, that the bosons satisfy commutation relations while fermions satisfy anti-commutation relations. So supersymmetry algebra is a combination of commutators and anti-commutators. And supersymmetry predicts various quarks, etc., etc. Next, transparency. Okay. If supersymmetry is a good symmetry, it predicts that the supersymmetric partners having different spin must have same mass. Unfortunately, till today, we have not observed a single supersymmetry particle in nature. So, therefore, it is not clear whether nature has the supersymmetry or not. And if at all it is there, it must be supersymmetry, must be badly broken symmetry. Because, for example, if it was a good symmetry, then we must have experimentally found an electron with spin 0. But till today, we have not found, and we can put a lower limit on its mass. So the question of the breaking of supersymmetry in high energy physics is a very difficult problem. And that's why in 1981, Witten suggested that we should maybe study supersymmetry breaking in quantum mechanics. And that started this field. And in last 40 years, supersymmetric quantum mechanics has given us deep insight in standard quantum mechanics. So I am not talking anything now beyond beyond standard quantum mechanics. So therefore, forget about supersymmetry in high energy physics, but supersymmetric quantum mechanics has its own, exists in its own right. Next, please. Okay. So what are the problems for which we have got deep understanding using supersymmetric quantum mechanics? Let us first solve the simplest problem in quantum mechanics, which I am sure all of the students here have learned, namely infinite square well. As we all know, infinite square well has only bound state spectrum, and the energy eigenvalues are given by En is equal to Cn plus 1 whole square, where n is 0, 1, 2, 3, 4. My question is, are there other potentials with similar energy eigenvalues? No textbook in quantum mechanics usually discusses such potentials with similar energy eigenvalues. I will show that in fact there are an infinite number of such potentials having similar energy eigenvalues. Next question. Another simplest problem rather in quantum mechanics is free particle. Nothing can be simpler than free particle because it has no bound state and a incident particle simply goes through. So that means there is no reflection, the entire thing is transmitted. In a technical language, if you calculate the transmission and reflection coefficient for free particle, the reflection coefficient is 0 at any energy and transmission coefficient is 1. Okay. So therefore, what people call this as reflectionless potential because reflection coefficient is 0. My question is, are there non-trivial potentials in quantum mechanics which are also reflectionless? Again, you will not find any textbook in quantum mechanics discussing this question. But by now we have found out, again, infinite number of reflectionless non-trivial potentials. What I am talking about are potentials having at least one bound state and still reflectionless. Okay. And I may not have time to say, but by the way, these reflectionless potentials have played an important role in soliton physics. Next question. With quantum mechanics, we find that there are few potentials which are analytically solvable, like one-dimensional harmonic oscillator, three-dimensional harmonic oscillator, hydrogen atom, and there are few other potentials. But all other potentials we can only solve by variational method or perturbation theory or numerical. So question is, what is so special about these several potentials which are exactly solvable? Okay. And a related question is, as I said, I am assuming that all of you have done one-dimensional harmonic oscillator. You will recall that that is the only problem in quantum mechanics which we can solve in two different ways. Number one, we solve 1D harmonic oscillator by solving Schrodinger equation. And second, we introduce the operator A and A dagger, so-called annihilation and creation operators. And without ever solving the Schrodinger equation, by simply using this operator method, we can solve the one-dimensional harmonic oscillator problem completely, right? And this, by the way, this again, I may not have time. A and A dagger method is extremely important because this is the whole basis of quantum field theory. Secondly, if you understand A and A dagger completely, you can also understand the basics of coherent states and squeeze states. Okay, coming back, the question is, what is so special about one-dimensional harmonic oscillator that we can solve it by A and A dagger method? Obvious question is, are there other potentials apart from one-dimensional oscillator which also we can solve by using this A and A dagger operator? Okay. I will show this in supersymmetric quantum mechanics that in fact we can do for an entire class of potentials which are called shape invariant potentials, and these shape invariant potentials include all these exactly solvable potentials in quantum mechanics. Next, please. Okay. Next question. We all study when we quantum mechanics, we realize that give me any potential, in principle, I can find out its eigenvalues, eigenfunctions, reflection coefficient, and transmission coefficient uniquely. Given a potential, the corresponding energy eigenvalues, reflection coefficient, transmission coefficients are unique, no matter who calculates it, right? My question is the converse true? That means, suppose I give you all the energy eigenvalues, and I give you reflection and transmission coefficients at all energies. My question is, can you tell me what is the corresponding potential? This is a very important area of quantum mechanics called inverse scattering, where by inverse I mean that given energy, reflection coefficient, transmission coefficient to construct the corresponding potential. It turns out the answer to the question is no. That means even if you give me energy eigenvalues and deflection and transmission coefficient, the corresponding potential is not unique. In fact, there are several parameter family of potentials having the same energy eigenvalue, deflection coefficient, transmission coefficient. So the obvious question is, then how can I find such a potential uniquely? The answer to that question is, apart from specifying energy eigenvalues, reflection and transmission coefficient, you must also specify normalization constant of at least one of the eigenvalues. This is called so-called normie constant. So once you specify that, then the potential is uniquely fixed. Okay. So now I can turn around this question and therefore ask, given any potential, how to construct one continuous parameter family of potentials with same energy eigenvalue, same reflection coefficient, same transmission coefficient. Again, by the way, no books in quantum mechanics ever will discuss this, that one-dimensional harmonic oscillator spectrum n plus of h bar omega is not a unique potential. But we can construct one continuous parameter family of potentials, all of which have the spectrum n plus of h bar omega. And they are distinct from harmonic oscillator. And this is true for all the solvable potential. In fact, you give me any potential with one bound state and give me its energy eigenfunction. Then I can immediately tell you, immediately construct one continuous parameter family of potentials. We have the same spectrum, same reflection coefficient, and same transmission coefficient as the starting potential. Finally, again, I may not have time to discuss, let me mention this. As we all know that WKB approximation in quantum mechanics, by construction, is exact for a large quantum number, but it does not do very well if the small quantum number is small. Okay. So the obvious question is, can we modify WKB approximation in such a way that it is not only exact for large n, but it is also exact for n equal to 0, that is ground state by construction. The hope is then that if you have got tightened it at both ends, namely it's exact at 0 and at infinity, then hopefully it will also do better in between. And the answer to that question is yes. Using this supersymmetry idea, people have constructed what is called a supersymmetric WKB approximation, which by construction is exact for the ground state as well as for the larger. And hence, it is found that where many of the key potential, it does better than the usual WKB approximation. Next, please. Okay. So now let me start with the formalism, and I will request the students to be patient for two transparencies, because that will be used in formalism, some mathematics. Okay. All right. So first, let me be clear here that unlike in high energy physics, whereby supersymmetry means the fermions and bosons are the supersymmetric partners, in supersymmetric quantum mechanics, there are no fermions or bosons. But by supersymmetry, we mean there are two Hamiltonians, let's say H1 and H2, and they are constructed such a way that there is an underlying supersymmetry. Okay, and I will show that the very fact that they are connected by this underlying supersymmetry ensures that their energy eigenvalues, eigenfunctions, reflection coefficient, and transmission coefficient are related to each other. That means if you know one of them, you will know immediately the other one. Okay. After discussing this, then I will discuss what I mentioned, the infinite square wave part, and show to you its infinite number of potentials which are the identical spectra with infinite square wave. Next, I will discuss this potential V of x equal to n into n plus 1 sec hyperbolic square x, where n is equal to 1, 2, 3, 4, and show that in the unit where h bar and 2m is 1, all this potential, if you solve Schrodinger equation, they're all reflectionless. But they have n bound set. That means if n is equal to 1, it has one bound set, n is equal to 2, it has two bound set, etc. Then I will also briefly discuss supersymmetry in 3 dimensions, how to extend. Initially, we will discuss supersymmetry in 1 dimension, and then I will discuss here how to extend to 3 dimensions. And then I will quickly introduce these shape invariant potentials, which include almost all the solvable potentials known in quantum mechanics, and show how their eigenvalues, eigenfunctions are known algebraically. Next, please. Okay. After that, probably I will not have time, but if time permits, I will construct strictly isospectral potential starting from any given potential. And finally, SWKB approximation, how it is exact by construction for larger and also for ground state. Thank you. Next, please. Okay. So as I mentioned, please be patient with me for 2 transparencies to introduce the formalism. Okay. And I am very careful in these 2 transparencies because I am putting everything h bar and m, everything. Okay. So let us consider an operator A, which is h bar by square root 2m d by dx plus w of x. W of x right now is an arbitrary function of x, and it is called as superpotential. But just right now take it as arbitrary function of x. So corresponding Hermitian conjugate A dagger is minus h bar by 2m d dx plus wx. Remember, d dx is anti-Hermitian because I d dx is Hermitian. Okay. So therefore, now let us construct 2 Hamiltonians, h1, which is A dagger A, and h2 is A dagger. Okay. So now remember one thing. When I calculate A dagger A, I have to be very careful about the ordering. Why? Because we know that d by dx and x do not commute. Okay. What one means is, when we say d of dx means there is acting on some wave function psi. So what I am saying is d dx, commutator of d dx and w of x acting on wave function psi is not 0. So that means, because we will get an extra term which is equal to w prime. Because when I apply d dx on psi, I get 2 terms, one is d dx psi plus dw by dx times psi. So this extra term dw by dx, you get extra. And when you take A dagger, since the ordering is reversed, you will get extra minus sign. So as therefore, students, I will encourage you to work it out in the simple algebra and see that V of x corresponding to the potential h1 is w square of x minus h bar by square root 2m times w prime. W prime means dw by dx. While V2 of x corresponding to h2 is w square x plus h bar by 2m square root w prime x. Okay.
Excuse me, sir.
Yes, please.
Yeah. So is W real?
Which one? W is real.
Okay.
W, yes. Okay, good. Thank you. Thank you for the question. Okay. So W of x is superpotential, and this V1 and V2 are what we call as partner potential. Remember, V1 has W square minus W prime, H bar 2 is there, and V2 is W square plus W prime. Okay. All right. Now I am going to show just this much. I am going to now show that all the energy eigenvalues of the Hamiltonian H1 and H2 are related. Similarly, the eigenfunctions, reflection coefficient and transmission coefficient of the 2 Hamiltonians are related. Next, please. Okay. Now, notice first thing. Since our Hamiltonian H1 is A dagger A and Hamiltonian H2 is A dagger, therefore, by construction, all their energy eigenvalues have to be positive semi-definite, because you can always write down, okay, take expectation value of A dagger A between psi and psi, so you can show that it is A psi mod square. Similarly for A dagger A. So this is the first important statement. all the eigenvalues of the Hamiltonian H1 and H2 by constructions is positive semi-definite. That means it can be zero but not negative. Okay. Now, suppose psi n1 is an eigenfunction of H1. What do I mean by that? That means H1 acting on psi n1, but H1 is nothing but A dagger A acting on psi n1 is equal to En1 by psi n1. That is the meaning of it is an psi n1 is an eigenfunction. All right. Okay. So now what we do is let us multiply this equation. Multiply A psi n1 by operator H2. That means you multiply by A. Multiply A dagger A on both sides by operator A. So what do we get here? A times A dagger A acting on psi n1 is equal to A times En1. But En1 is a number, so I can flip it and write down En1 times A times psi n1. So my equation is A dagger A psi n1 is equal to En A psi n1. But we know that A dagger A acting on psi n1 by construction. Okay. So let me go back one step below. Let us start with H2 and suppose please go back to the word transform. Here it is. Sorry. Now let us consider H2 and let us say corresponding wave function is psi n2. So therefore, what do we know? That A dagger acting on psi n2 is En2 acting on psi n2. Agreed? But now you see, compare with the previous step. So what do we find here? H2 acting equal to A dagger A psi n1 is equal to En1 psi n1. Therefore, we find that H1. We can say therefore H1 acting on A dagger psi n2, right? Because A dagger psi n2 is this. Is A dagger psi n2 is equal to En2 times A dagger psi n2. So what we have found that so what we have proved therefore is that En1 and En2 must be equal because both have the same eigenvalue. Because remember H1 acting on psi n1 should En1, but I just now proved that H1 acting on A dagger psi n2 is equal to this, but it has to be same as this En1 by this step. Therefore, the two are equal. Except one place. The proof breaks down if A acting on psi n, if A acting on Now, if proof breaks down if A acting on psi 0 1 equal to 0. You may ask me why I am saying psi 0, because we have seen that already that En1 En2 are greater than 0 or at most 0. But if it is 0, it has to be ground state. Therefore, if this proof breaks down, it has to be for the ground state. Okay. So therefore, there are two possibilities. Either A acting on psi 0 1 is equal to 0 or A acting on psi 0 1 is not equal to 0. Okay. So
does that mean this theory
remember,
is
I want you to recall this similar step in one-dimensional harmonic oscillator, where instead of capital A, we have small a, and we say that to know the ground state wave function, what we do? We act small a acting on ground state wave. So instead of small a, we are only doing it by capital A. That's the only difference. Okay. Next, please.
Can I ask a question?
Yes, please.
So does that mean this theory is applicable to the excited states, not on ground states?
No, I'll come to that in a minute. Very good question. I'll come in a minute. In fact, this is a very good question. Just in fact, next transparency, you'll get the answer. Okay. So as we saw the last transparency that all the energy eigenvalues are related. In case A acting on psi 0 1 is not equal to 0. But if it is equal to 0, then what happens? Ground state energy of the first Hamiltonian is 0. Ground state energy 0. Therefore, the corresponding wave function is single. But all other excited states in the energies are non-zero, they must be paired. So therefore, your answer to the question is, in this case, we find that En of 2 is En of n plus 1 1. Why? Because its ground state energy of 1 is 0. But what about this first excited state? We don't know. But it must be same as the ground state energy, ground state of En2, because we know that all states are paired. So immediately we know one thing, that the ground state energy of the first Hamiltonian is 0, and the all other states of Hamiltonian H2 and H1, the eigenvalues are related by this. Next, can you go to one transparency before? Yeah. Now notice here one thing. From this fact here, we immediately know that A sin 1 is the eigen function of H2 and A dagger sin is the eigenfunction of H1. Next, please. So from here, I also know that sin 2 is the normalization factor times A times sin plus 1. Okay. That means, now this is very important step. What it means is that if I know the first excited state of first Hamiltonian, by applying operator A, I can get the ground state wave function of sin 2. Or conversely, if I know the ground state wave function of sin 2, I can get first excited wave function of the grounds this one state by applying A dagger and sin 2. Okay. So therefore, summarizing, what we have shown that if the two Hamiltonian H1 and H2 are related, are given by A dagger and A dagger, in that case, if A acting on psi 0 equal to 0, in fact, I am going to assume this throughout my lecture, that A acting on psi 0, 1 is always equal to 0. So for the ground state energy of first Hamiltonian, by construction is always 0. And the rest of the eigenstates of second Hamiltonian and first Hamiltonian, they are related by this formula. And the corresponding wave functions are also related by each other. Okay. Now, okay. Now recall the operator. Recall the operator psi 0. Let us consider the equation A times psi 0 equal to 0. Okay. Now, what is the operator? Please go back to the previous transparency. Or even still further, A. Further, one down. Yes. Remember, A was H minus the H bar by 2, not minus, H bar by 2m, the dx plus wx. Now we are saying A acting on psi 0 1 equal to 0. That means this operator acting on psi 0 1 equal to 0. That means d psi 0 by dx plus w times psi 0 equal to 0. So we can solve this equation. Go back now to the, go further. Yes. No, one down, one down. Yes, thank you. So now you see, so now I can from here immediately calculate W. Why? Because from that equation, A acting on psi 0 1 equal to 0, we immediately find that W of x is equal to minus h bar by square root 2m psi 0 prime upon psi 0. Right? Now this equation actually is very important. Why? You can look upon it in two different ways. Namely, if you know ground state wave function of any potential, you can immediately calculate its first derivative and divide it by psi 0 1, and therefore you immediately know the corresponding superpotential W. Right? So this is very, very powerful. You take any problem in quantum mechanics, just if you know its ground state wave function, you know the corresponding superpotential W. Once we know superpotential W, you can construct the two partner potential, and therefore just knowing the ground state of potential 1, you have therefore constructed a new potential H2, which is A dagger, and all its eigenvalues and eigenfunctions, just now we saw, are related to that of the first one. So this is a very easy thing. I'll encourage students that go back home today and do take three-dimensional harmonic oscillator, hydrogen atom, any problem, and try to do this exercise and to discover for yourself new potential in quantum mechanics whose spectrum is same as the 1D oscillator. Of course, as I said, all this is discussed in detail in my lecture notes. Okay. Second thing, on the other hand, if I don't know ground state wave function, but if I know W, then I can easily obtain ground state wave function from here, because psi 0 prime by 0, I can immediately integrate both sides, and therefore you immediately find that the ground state wave function is nothing but, apart from normalization, e to the power minus w of y dy integrated and limit is x. So therefore this equation, as I mentioned, has two different meanings. One, given the eigenfunction, ground state eigenfunction, you can immediately calculate w and hence partial potential. On the other hand, if you know the ground state wave function, then you can immediately, if you know the superpotential w, then you can immediately integrate and calculate the corresponding ground state wave function. Okay. Okay. Next question is, I consider that, just 1 minute. I consider the case where A acting on psi 0 or equal to 0. One obvious question students will ask is, instead of A acting on psi 0 or equal to 0, I can also consider A dagger acting on psi 0 2 equal to 0. The question is absolutely right. Only thing is, we can't simultaneously have both these cases. Either you can have this or you can that. Why? Because as we now saw, just now we saw, if this first is true case, then my corresponding eigenfunction is minus wi dy. On the other hand, if A dagger, this is equal to 0, because A dagger has an extra minus sign. The psi 0 2 has a plus sign here. Now you know that only one of them can be square normalizable and square integrable. So it's up to you to choose whether you want to have this as square integrable or you want to have this as square integrable. So as a matter of convention, we always choose such that psi 0 is the ground state wave function. This is a matter of just convention. So you can choose either this or that. But as a matter of convention, we always choose. Okay. All right. Next. Okay. So now onwards, no mathematics. But whatever result just now we have proved, now try to get various conclusions from here. For standard quantum mechanics. Okay. First thing, what have we learned? We have learned that with our formalism, the ground state energy of first Hamiltonian is always equal to 0. And its wave function also we know if the corresponding superpotential W is known. Number 2, we know that all the other states of the two Hamiltonians are paired. That means the first excited state of the first energy of first Hamiltonian is same as the ground state energy of the second Hamiltonian. The second excited state energy of first Hamiltonian is same as the first excited state about the second Hamiltonian. Second thing we also learned that if you know any wave function here, say first Hamiltonian, you can immediately obtain the corresponding wave function of the second Hamiltonian by simply applying the operator A on the corresponding wave function of the first Hamiltonian. On the other hand, if you know the wave function of the second Hamiltonian, you can immediately obtain the corresponding eigenfunction of the first Hamiltonian with the same energy by applying A dagger onto the corresponding eigenfunction of the second Hamiltonian. Okay, so this is the broad summary of what we have done so far. That using this A dagger and A dagger formalism, we have shown that the two Hamiltonians A dagger A and A dagger, which we call H1 and H2, are always such that the ground state energy of H1 is 0 and all other energy eigenvalues of the two Hamiltonians are related. Not only eigenvalues but also eigenfunctions. Also, if knowing of one, you immediately know eigenfunction of second, except for the ground state, which lies alone. Okay, next please. Okay, now just for a curiosity, because you know physics doesn't have magic. There is no magic in physics. So anything which happens, there must be a reason for it. And in this case also, the fact that this seemingly different Hamiltonian H1 and H2 have the same spectrum except for the ground state and the eigenfunctions related, etc., is because there is actually an underlying supersymmetry. So now this is, you can understand what one means by supersymmetry here. So let us construct a capital Hamiltonian H, which are the two diagonal elements H1 and H2. So H1 is A dagger A, H2 is A dagger, and the diagonal elements are 0. And now let me construct two operators Q. So this is Q is a 2 by 2 matrix 0, 0, A and 0. And hence Q dagger is 0, A dagger 0, 0. Now let us calculate commutator of H1 and Q. I want all of you students, using the fact that H is A dagger A and Q is as given here, please go home, calculate this commutator and convince yourself that it is 0. It is very simple. Similarly, type H and Q dagger. So okay, this H is H, and where this is A dagger, this is A dagger, and Q dagger is A dagger, and show that this is also 0.
Excuse me, sir. Is this
Yes.
commutator or anti-commutator?
Commutator. This is commutator. If it is anti-commutator, I will tell you in a minute. Right now, it is just commutator. Next step, I am going to tell you is anti-commutator. Okay. So next step is, please check the anti-commutator of Q and Q dagger. That means Q dagger plus Q dagger, and show that it is equal to 0. Similarly, similarly Q dagger and Q dagger anti-commutator. That means Q dagger square is equal to 0. You can immediately see Q dagger square is 0. Similarly, you can immediately see Q square equal to 0. So these are the two trivial anti-commutations. What is non-trivial is the anti-commutator of Q dagger. That means calculate Q dagger and calculate Q dagger plus Q dagger, and you will find that you will exactly get this answer. So this is the non-trivial part of supersymmetry algebra, and we call it supersymmetry algebra because it has the commutators and it has the anti-commutators. So this is the supersymmetry algebra at the level of supersymmetry quantum mechanics. When we go to quantum field theory and particle physics, it's just a generalization of these ideas that you will again find for bosons commutation relations, for fermions anti-commutation relations. Okay. All right, next please. Okay, so now let's start the applications. Okay, so first application, which all of you have done, okay, namely infinite square wave. What is infinite square wave problem? We all study that infinite square wave problem is one where potential is 0 when particle lies in the well. That means, and the well we usually take in the textbook to be lying between 0 and L. Okay, and the potential is outside to be infinity. So that's why we say the infinite square wave. All right, and all of you have studied these problems, and we have known that very well. That's eigenvalues are n plus 1 square h bar square pi square by 2 ml square. So in particular, its ground state energy is n equal to 0. Is h bar square pi square by 2 ml square. Okay. So what is the recipe? So now you see this is only one Hamiltonian, but I know its ground state wave function also. So therefore, starting from the ground state wave function of infinite square wave, I want to construct now two partner potentials, of which H1 by construction will be my infinite square wave, but H2 will be a new potential which you have never seen in your life, as you will see in a minute. So what is the recipe for construction H1 and H2? We know that for construction the ground state energy of H1 is 0. Therefore, we can immediately say that H1 is nothing but is equal to the infinite square wave Hamiltonian minus its ground state energy. Since I have subtracted ground state energy, therefore by construction the energy ground state energy of H1 is 0, and the energy eigenvalues of the H1 are therefore n plus 1 square minus ground state energy, so which is nothing but n into n plus 2 h bar square pi square by 2 ms. So okay, so therefore I have already constructed for you H1. All right, and now I will come back to operator construction, but that H1 we already know without doing anything. Its eigenvalues are En1 is this. Now as per what are the wave functions of H1? Since the two Hamiltonians just differ by constant, all their eigenfunctions must be proportional to each other. So therefore the eigenfunctions of the Hamiltonian H1 is the same as the infinite square wave, namely 2 by and the same normalization sine n plus 1 pi x pi. Okay, so thus for H1 we know the energy eigenvalues and eigenfunctions, and since we know its ground state wave function, next transparency. Okay, since we know its ground state wave function, we can immediately calculate W. Okay, So W therefore is minus h bar by 2m. Remember psi 0 was basically sin x. Therefore psi 0 prime will be cosine x. So this will be cosine x by sin x, basic nothing but cotangent of x. These factors you can immediately check, trivial these factors. So we find that for W of x is apart from these factors cotangent of pi x by L. Now that knowing W, we immediately can construct V2. Because what is V2? We have already seen that V2 is nothing but W square of x minus h bar by square 2m W prime of x. So just plug it in here. And remember that cotangent square is, what is cotangent square? Is equal to cosec square minus 1. So you can immediately write down the whole thing in terms of cosec square x. So therefore this is the H2 potential is this. And the corresponding Hamiltonian is of course the potential plus the kinetic energy, namely d minus d2 dx. I want to ask all of you students, have you any time ever seen this potential? And by now we know its all energy eigenvalues same as infinite square well, except the ground state. But since infinite square well has grounds has infinite number of eigenvalues, even if I subtract one eigenvalue, the new potential also has infinite number of eigenvalues. Okay, this is very remarkable. All right. Now we can immediately also calculate its ground state wave function, for example. How? Because we have seen that the ground state wave function of second Hamiltonian is nothing but operator A acting on the first excited state wave function of the first Hamiltonian. But we know that the first excited state wave function, you know exactly, right? Sine 2 pi. So using that exactly, you can apply this and you can show that the ground state wave function of the second Hamiltonian is sine square pi x by L. Remember that like sine pi by x, it exactly vanishes only at the two boundaries, namely x equal to 0 and x equal to L. On the other hand, you can also calculate, for example, its first excited wave function, which is nothing but A acting on the second excited wave function of the first. Okay. And what do you find? You find this is equal to sine pi x times sine 2 pi x. Now notice, this wave function has one node. Why? Because sine pi x by L vanishes at x equal to 0 and L, but sine 2f pi x by L also vanishes when x is equal to L by 2. So therefore, it has a one node. So in this way, you can construct second, third, fourth, fifth excited state. But the remarkable fact is, therefore, we have discovered a new potential which you have never seen in life before, having essentially the same spectrum as 1D oscillator, having infinite number of bound states, and we know everything about this potential, all its eigenfunctions, eigenvalues, everything. Next. Okay, but now I can play the same game again because my Hamiltonian H2, I know its eigenvalues, ground state energy eigenvalue, because ground state energy eigenvalue is same as the first excited state energy of the second. So what I can do is, I can construct the new W1 immediately. Why? Because I know its ground state wave function of second Hamiltonian, and therefore I can immediately calculate the corresponding superpotential, and in this way I can find that the third potential you get, again new potential, is the same cosec square, but coefficient is different, 6. That's all. That's the only difference. Okay. And in this way, you can now go on and on and on and construct one continuous parameter family of potentials, which is equal to P into P plus 1 cosec square minus P square. And minus P square I have added here so that by construction its ground state energy will be 0. Now the beauty about this, remember this, the beauty about this potential is energy, all energy eigenvalues are all known. All eigen for any P. Okay, and P you can take any value 0, 1, 2, 3. And the corresponding wave, the ground state wave function for any P is sine P plus 1. Okay, so even if you take P equal to 0, you get sine x for the infinite square well, etc. etc. So therefore, summarizing, we have seen the first application of SUSY quantum mechanics, namely which none of you have seen, that by starting by infinite square well, we are able to construct one continuous parameter family of potentials, all of which energy eigenvalues and eigenfunctions are essentially similar to 1D oscillator, and they are all known algebraic, analytically, without doing any work. Isn't it fantastic? Go to next. Okay. Now onwards, so far I was very careful and I put an H bar and 2m, etc. But now onward, just to simplicity, we can always do that. But simplicity, I will just remove H, assume from now onwards that H bar and 2m equal to 1. So the algebra doesn't have to every time you write H bar and 2m, etc. Okay. Okay. So now what I want to show you is that the free particle is not the only potential having reflectionless. This is reflectionless. Namely, I am going to construct for you one continuous parameter family of potentials, all of which, not continuous, but one parameter family of potentials, all of which have this bound state, but reflection coefficient is 0 at all positive rates. All. Okay. Okay. For simplicity, I will assume here that my potential is symmetric. Actually, need not do that, but for simplicity, I am assuming here. In my lecture notes, you can find for the general case. So let me consider because as we know in supersymmetric construct quantum mechanics, once we know V1 and V2, we know corresponding superpotential W. So let us start with two potential V1 and V2, which are both discrete spectrum and continuous spectrum. That means they are scattered. And let us assume that the corresponding superpotential as x goes to plus infinity is W plus, and x goes to minus infinity goes to W minus, and since it is symmetric potential, W minus is minus W plus. Question is, what are the corresponding V1 to as x goes to plus minus infinity? Okay. So since V12 is this W square W prime, and this vanishes, so this is nothing but W plus square, because W minus square is W plus. Okay. So therefore, since W goes to W plus, we want to remember where W square minus W prime, but W prime naturally vanishes if W is a constant asymptotically. Hence we have this. Next, please. Okay. Now I hope some of you at least have done the scattering problems in one-dimensional quantum mechanics. So what do we do there usually? We assume that there is an incident plane wave e to the power I kx coming from left, having energy E, and okay. And then what can happen is, if there is a potential, it experiences a potential. It can happen that a part of it gets reflected and part of it gets transmitted. In this problem scattering problem, we are only interested in knowing what happens to the wave function asymptotically, namely what happens as x goes to minus infinity and x goes to plus infinity. Remember that the reflected wave will go to minus infinity. The transmitted wave will go to plus infinity. So what happens to x goes to minus infinity? So what can happen? We have got already the incident wave is there, that will always remain. But the reflected wave will be e to the power minus kx by kx, because going to reflected side. On the other hand, the incident wave, if it is transmitted, it will go same as e to the power kx, but multiplied by a factor t1. Because of the potential, it may get affected by some factor t1. And our job is how to calculate this factor R12 and T12. By the way, R1 and T1 means for first potential, R2 and T2 for the second potential. And I will show that the reflection and transmission coefficients of two potentials, partner potentials, are related to each other. And it's easy to see that K is nothing but E minus W plus square. W plus square is the value of the potential at plus minus infinity. Because why? Because you know that the V is equal to W square minus W prime, and W prime vanishes. So therefore this is the case. Okay. So now let me show you that the supersymmetry connects continuous wave functions of H1 and H2 having same energy. Next, transparency. Yes. Okay. So what is psi2? By psi2 is nothing but the normalization types A acting on psi1. And what is psi1? Normalization type A dagger acting on psi2. Right? Because we know that this is by definition. Psi2 is up to normalization. Now, this is our reflected ray. Okay. So this I can say is equal to minus n times A acting. So this is my psi1 minus n times psi1. So therefore you take the differentiation of the psi1 and you get ik plus w plus ik minus w. Similarly, you calculate T1 acting on this one and you get minus n times this. Okay. Remember, so therefore, remember there is a. So that derivative comes because of the derivative term you will get these factors. Yeah. Okay. All right. And so now, if you compare the two, you immediately find from here, because divided by the normalization factor, therefore you immediately find here that the reflection amplitude, remember this is amplitude, is minus I minus w upon I plus w. Okay. And the transmission amplitude is minus of ik minus w plus upon minus ik minus w. But w minus we have already seen because symmetric potential is equal to minus of w plus, so that's why I written w. I already used here this fact that w minus is the same as minus w plus. So therefore, this is the expression we get. So what have we found out that part? That the reflection coefficient of first and second Hamiltonian are related. Transmission coefficient of two Hamiltonians are also related. All right. Next, please. Okay. Okay. So just go back one step before. Okay. So what does he find here? If I find that if reflection coefficient of one of the potential is 0, then automatically without doing any calculation, I find that the reflection coefficient with the other potential is also 0. Okay. So now this immediately tells me what to do. Namely, if I can choose my W etc. such that one of the partner potential is a free particle, then I immediately know the corresponding partner potential will have one bound state. That's the trick which we're going to do. Okay. So now let us see how to do that trick. Next, please. Okay. So now this is a bit of a, called intuition, because this is not straightforward. So I am just telling you to do this. Let me choose W of x is equal to B times tan hyperbolic x. Remember, tan hyperbolic is nothing but sine hyperbolic x divided by cosine hyperbolic x. And I hope all of you know the hyperbolic functions. So given W of x, we can immediately construct the corresponding to partner potentials. What is V1? B square minus B into B plus 1. And you remember tan hyperbolic square is 1 minus sec hyperbolic square. So if you use that fact, and remember sec hyperbolic is nothing but 1 by cos hyperbolic. So therefore you find that the partner potential V1 is B square minus B into B plus 1. And V2 is B square minus B into B minus. This is the important point. This is B minus. So now it tells you immediately what I should, because B is an arbitrary parameter B. So immediately tells me what I should choose for B. Right? Obviously I should, if I choose B equal to 1, then you find that V2 is equal to 0. That means V2 is equal to, that means V2 is a free particle. If V2 is a free particle, by construction V1 is a potential having one extra bound set. So therefore, without doing any calculation, we have found this potential V1, B is 1, so is equal to 1 minus 2 sec square hyperbolic square. So without doing any calculation, I have shown you here that you please go back, solve Schrodinger equation for the potential 1 minus 2 sec hyperbolic square x in the unit where h bar and 2m equal to 1, and you will find, and calculate the reflection coefficient, transmission coefficient, you will find that it is a reflection-less potential. That means its reflection coefficient is 0 at all energies. But not only that, since we know that the transmission coefficient for the free particle is 1, so we immediately know the transmission amplitude for this potential minus 2 sec is equal to minus ik minus 1 upon ik plus 1. Isn't it a magic that just starting from here, immediately I know, choosing B equal to this, and I get a potential which is reflectionless. Okay, but now I can do the same trick again here, because if I choose instead of b equal to 2, if I choose b equal to 2 now, I will get a potential 2 times 1, which is 2. So therefore now V2 will be 1 minus 2 sec square x, and the corresponding V1 will be 6 hyper square. So go back to the next transparency, please. So, okay. So now, okay. So before that, I've just forgot. Let me repeat again. So by starting from free particle and choosing, we have shown that there's a new potential V1 which is reflectionless, which is 1 minus 2 sec hyperbolic square x. It has exactly one bound state at e equal to 0, and the corresponding ground state wave function apart from non-relation is sec hyperbolic x. Now, as I said, immediately you can generalize and get next will be 6 sec square, then 12, etc. And in this way, you can show that there's a one parameter family of potential given the p square minus p into p plus 1 sec hyperbolic square x, where p can take any value from 1, 2, 3, 4, 5, 6, and it has p bound states, and it is reflectionless at all energies, and corresponding transmission amplitude also we know analytically, because from T1 we can do T2, T2 from T3, and so in this, remember, I hope all of you know what is gamma function. Okay, you can explicitly write down the transmission amplitude for this potential in terms of the ratios of the gamma function, and its ground state eigenfunction for ADP is this. First exercise wave function again using supersymmetry formalism is this. So in this way, we have found the power of supersymmetric quantum mechanics, that just using this formalism, number one, starting from infinite square, we were able to obtain infinite number of new potentials with essentially the same spectrum. Number two, starting from free particle, we are able to construct one continuous parameter family of potential, all of which are reflectionless, and they have finite number of bound states, unlike free particle which are zero bound state. Next, please. Okay. Going to three-dimensional analysis is very straightforward. All of you, if you have done any problem in three-dimensional quantum mechanics, what do we usually do? That we assume that the wave function for three-dimensional problem with a spherical symmetric potential is the RNLR divided by R, this is the radial part, and the angular part is YLN theta phi. And once we take out the YLN theta phi, we all learn that the radial part RNL satisfies a one-dimensional like Schrodinger equation. Remember, one-dimensional like, except that now in the potential we get an extra term, so-called centrifugal barrier, which is L into L plus 1 by R square. But this is a one-dimensional like equation. So therefore, I can immediately extend all the machinery of 1D SUSY quantum mechanics to this potential. Okay, and treat it as if this is a one-dimensional problem, and therefore everything goes through. Only except for two changes. If you start with any three-dimensional potential, you must consider effective potential is this VR plus this. You just can't, you just take alone VR. Number two, one-dimensional problem which we are doing, x was going from minus infinity to plus infinity. In this case, remember R always goes from 0 to infinity. So, but for these two changes, everything is identical. As an application, I will encourage all of you students, start with three-dimensional oscillator. And I am telling you that corresponding WR is this. You can also work out yourself. And from that, you can discover SUSY. You can do all the SUSY formalism for these two potentials and discover new potentials which you never seen in your life from starting from here. Next, please. Okay. I hope, how much time I have, Prashant? How much time more left? Anybody?
I think you can yeah. How much time?
Sir, he can give for another 5 to 10 minutes.
Okay, 10 minutes. Sure, thank you. Okay. So now I am coming to, in fact, perhaps the most important application of supersymmetric quantum mechanics. Namely, I want to show you several things here actually. Number one, that the operator method for one-dimensional oscillator using A and A dagger we can generalize it a class of potentials that shape invariant potentials. And number two, for any shape invariant potential like 1D oscillator, I can just calculate its eigenvalues and eigenfunctions in 2 minutes without doing any calculation. Okay, it's just so easy. So again, you have to please bear with me for one transparency. Okay, for mathematics. Rest will be application. So let us consider two potential V12 X and A1, and they are the partner potentials. Okay, what do we mean by partner potential? Partner potential means V12 of X and A1 I can write down as W square minus W prime, and V2 as W square plus W prime. By the way, X is our usual X, and A1 is a parameter of the problem. Like 1D oscillator, the parameter is the omega, three-dimensional oscillator problem. Okay, similarly in the hydrogen atom, etc. Alpha is the problem, A1 there, etc. So A1 is the parameter of the problem, but otherwise V1, V2 are partner potential. Now we call these potentials as shape invariant. If, notice this part, this is a very subtle point here. If I can write down V2 of X and A1 as equal to V1 of X and A2 apart from a constant. Remember, subtle point, V2 and V1 are X and A1. But what I am going to say that if it is shape invariant, if V2 of X and A1, I can write down as V1 of X and A2 up to a constant. Okay. If this is satisfied, then I call the two potential to be shape invariant. Why shape invariant? Because by just changing the parameter A1 to A2, the potential essentially retains the same shape as V1, apart from a constant. Because we know if you add a constant, it doesn't change. So that is why we call these two potential as shape invariant. But okay. Now this is a very subtle, very, very important step. In fact, a very deep step. The interesting point is all the known solvable potentials of quantum mechanics, in fact, have this property. But this property was never recognized for 80 years of quantum mechanics. It was only recognized after supersymmetry came by famous work of Gandenstein in 1983-84, and then we took further the work of Gandenstein that and showed that all the known solvable potential of quantum mechanics actually have this property. Okay. Now you will ask me, what is this A2 compared to A1? Because remember I said A1 is a parameter of the problem. So A2 is also a parameter of the problem, but it could be any function of A1. And RA1, as I said, is a constant independent of X. Okay. So our formalism, we always have assumed that we have started the partner potential V1 and V2, where by construction V1 is such that its ground state energy is 0, and its ground state wave function I always know, right? And then we can construct whole machinery for other cases. So therefore, since I know V1, X and A1, I immediately know that E0, a first potential as a function of A1 is equal to 0. I also know the corresponding ground state wave function of V1 as a parameter of A1. Remember this, A1 is very important. So please remember this. Apart from normalization is equal to W1 via A1 dy, upper limit X. Okay. Now if the two potentials are related by constant, I can just add the kinetic energy, namely minus h bar square by 2f d2 dx to both the potentials. So therefore, this shape invariant definition also I can write down as definition for Hamiltonians. That the two pattern Hamiltonians are related by the same part, namely h2 of x and a1 is equal to h1 of x and a2 plus a constant. But we know that h2 by x and a1, okay, we know there are a dagger a and this is a dagger. But now h1, what is h1 of x and a2? Is a dagger a2, a2. That means I am saying that h2 of x and a1 is equal to a dagger x2, ax2 plus a constant. Okay. Now second point notice, since these two Hamiltonians differ by constant only. That means that all the eigenvalues of the two Hamiltonians must be same apart from this constant. So in particular, therefore, the ground state energy of the second Hamiltonian as a function of A1 is the ground state energy of the first Hamiltonian as a function of A2. Remember, plus this constant. And since the two Hamiltonians differ by constant, all the eigenfunctions, for example, the ground state eigenfunction of the second Hamiltonian as a function of A1 is proportional to the ground state wave function of the first Hamiltonian as a function of A2. Right? So remember, these are the very important steps. Okay, next please. Yes. But now, if I change x A1 to A2, the corresponding wave function will be e to the power wy A2. Now, A2 is, suppose A2 is such that the corresponding eigenfunction is square integrable, then I know by construction that E01 of A2 is equal to 0. Right? Because I01 of x and A2 is nothing but W of y and A2. And if A2 is such, this is big if A2 is such that it is square integrable, then in that case I know the wave function, ground state wave function, and the corresponding ground state energy 0. So this big if is if A2 is such that this is square integrable. And that fact, we'll see this is very important point. So therefore, let us assume that we have A2 is such that this is square integrable. Hence, can we go back to one step before? Okay. All right. Now remember this step. So please next. Yes. So now, so therefore the first excited state energy of the first Hamiltonian, which is same as the ground state energy of the first Hamiltonian, is Ra1. Right? So the A0, but this is by construction equal to E02. Therefore, we have proved that this innocent looking factor Ra1 is nothing but the ground state energy of the second Hamiltonian at A1. Remember this fact. Please go back to previous transparency. Again, I want to emphasize this important point. Yes. Remember, the ground state energy of this E02 is same as ground state energy of 1, a function of A2 plus Ra1. But just now we have shown that ground state energy of A2 is equal to 0, so long as the corresponding eigenfunction as a function of A2 is W is this integral is square integral. And hence this is the 0, therefore this is equal to Ra1. Right? Next. So therefore, without doing any work, just by this fact, we have found that the ground state energy of the second Hamiltonian, which is first excited energy of first Hamiltonian, is Ra1. And now we can also know the first excited wave function of the first Hamiltonian, which is equal to A dagger acting on psi02. Therefore, this is equal to A dagger psi xi01. So therefore, we immediately also know the ground state wave function of the second Hamiltonian. Okay. So therefore, if the potential satisfies that innocent looking shape invariance property, without doing any calculation, we know the first excited state eigenfunction and eigenvalues. Next, please. So now we can repeat this procedure because since the second Hamiltonian has, we know all its energy eigenvalues, subtract and take construct third Hamiltonian, and again it will have the same property. So in this way, you will find that the En1 is equal to sum of k equal to 1 to n Ra k, and the corresponding all the energy eigenvalues will be known. And the corresponding eigenfunctions will be. Now this is where, can you go back one step before, please? I want to all of you to please look at this step very important step here. Okay. How do we calculate usually in one dimension, one harmonic oscillator? We say that the first excited state wave function of harmonic oscillator is nothing but the A dagger acting on the ground state wave function, right? Oh, there is a typo here. There has to be A dagger. Okay. So therefore, in this case, what we have found, very subtle point here. We have found that the ground state wave function of the second Hamiltonian is nothing but A dagger, acting on A1, but psi 0 of 2. So only difference is, so therefore this expression is same as that for 1D oscillator, except that instead of in 1D oscillator, A is the same everywhere. A1 is equal to A2, we can prove that. In other cases, it is A2 is not same but A1. That's the only difference. Next, please. And therefore, in general, by starting from the okay, we can construct therefore all the excited state energy eigenvalues of the new Hamiltonian, A dagger, A dagger, A dagger, etc. Similarly, one can show that the corresponding reflection transmission coefficients of the two supersymmetric shape and potential related by this formula. Okay. So in this way, if the potential is shape invariant, knowing the reflection transmission coefficient, energy eigenvalues, energy eigenfunction of one Hamiltonian, we know everything about the second without doing any calculation. In 2 minutes, we know everything. Okay, now this all may look very, very boring. So let us do examples. Nothing like doing example where you can see the simplicity. So please, next transparency. Okay. So let me start the same example which we had done for the free particle case. Remember. So start with W of x, B of tan hyperbolic x, and calculate V1, V2, which we already did there. And we had seen that V1 was B square minus B into B plus 1 sec hyperbolic square x, and V2 was B square minus B into B minus 1 sec hyperbolic square x. I want you to look at this too carefully. I am going to show you that these two potentials are shape invariant. That namely, I am going to show you that V2 of x and B. Now let us see V2 of. How can I write down V2 of x and B as V1? Notice that I can write down V2 as V1 if I change B to B minus 1. If I change B to B minus 1, okay, here, if I start with V1 and change B to B minus 1, B to B minus 1 goes here, B plus 1 goes to here. So therefore, if in V1, if I change B to B minus 1, I will immediately get V2. So in this way, we find that V2 of x and B is B square minus B into B minus x square. Thus, V2 of xB is V1 x B minus 1 plus, this is the important part. You see, we change B to B minus 1, so this factor becomes B minus 1 square. But actually, I have got B square. So I must take into account that. So V2 of x and B is V1 of x B minus 1 plus B square minus B minus 1 square. So this innocent Lakey factor is nothing but, in our case, is B square minus B1 square. So therefore, in our case, A1 is B, A2 is B minus 1. So RA1 is B square minus B minus 1 square, which is A1 square minus A2 square. So we can immediately generalize, and therefore, from A2 will be equal to B minus 2, and so on and so forth. And so therefore, E and B, you can just keep on adding A1 square minus A2 square, A2 square minus A3 square, A3 square minus A4 square. So all these will cancel, and you'll get A1 square minus An square, N plus 1 square. So you'll find that the nth eigenvalue of this original Hamiltonian is B square minus B minus N square. So you see, knowing the ground state eigenvalues, we know all the eigenvalues of this Hamiltonian. And therefore, we know corresponding eigenfunction, sec hyperbolic B square. And therefore, we know, therefore, psi 1 is A dagger this. So you know all the first excited wave function and so on. So therefore, if a potential is shape invariant, just given this, I need not know its, I can calculate all its eigenvalues and eigenfunctions by just start knowing its ground state, eigenvalue and eigenfunction. Okay. Second example. Let's go to the next. One more example. Okay, maybe I don't have time, so I will skip that. So in this way, this is a problem for your students now. Please go to my lecture note, 2004 lecture notes I gave the reference. There are 7 or 8 potentials there given, like one-dimensional oscillator. Yes.
Excuse me, sir. Sir,
yes.
You may continue for some more time because our
okay. Thank you very much. Good.
Actually, she's not available today, so you may continue
wonderful.
for some more time. Then we can have a discussion session.
Yes. Thank you, madam. Thank you so much. Okay. So you can immediately therefore see that corresponding to this, we have got this Coulomb potential, 3-dimensional oscillator, 1-dimensional oscillator, Morse potential, Rosen-Morse potential, Rosenberg's two potential, all are there. Also Eckhart, Scarp 1, Scarp 2, Posteller 1, Posteller 2. They're all shape invariant potentials. And please go to my lecture note. I had shown this for example. But it is best for students to take this and explicitly see for yourself at least 2-3 examples that they are all shape invariant. And with translation, that is important. Last transparency, please. Last time, you see, we found that there's this one. We found that their shape invariant is b going to b minus 1. That means translation of parameter by constant. In next one. So all the potentials which are there in the literature, all of them, these potentials are shape invariant with translation. That is the beauty. Okay. Next transparency, please. So so now the next problem. This is by the way again something which I'm going to tell you. No quantum mechanics books discusses this, but it is very easy. Namely, you give me any potential, just tell me its ground state wave function, and I can construct for you immediately one continuous parameter family of continuous. Remember the word continuous parameter family of potentials whose energy eigenvalues, reflection coefficient, and transmission amplitude at all energies are identical to the original potential. Okay. Namely, okay, as we have first, we had already, inverse scattering has told us that if you just give me energy eigenvalues, reflection, and transmission complete, corresponding potentials are unique. That's the reason why we are able to construct a one continuous parameter family of potentials which have the same energy eigenvalues, reflection and transmission coefficient same, but their eigenfunctions are same, different, and then the normalization constant for the say ground state wave function is 0, different for all this. Okay, all right. So the same question what I'm asking is in supersymmetric quantum mechanics languages. If I give you a superpotential W, you know that the corresponding potential V1, 2 are unique because V1 is W square minus W prime and V2 is W square plus W prime. They are unique. And once a potential is unique, all its energy eigenvalues, eigenfunctions, reflection, transmission, everything is unique. Question I am asking today is converse true? That means I am not giving you W, but I am just giving you one of the potential V2. I am giving you V2 and asking you a question. Is the corresponding potential V1 unique? In other words, given V2 is W unique and hence V1 unique? And the answer to the question in fact is no. And the reason for this is something very fundamental, which again students, unfortunately so far what you people ever have studied is what is called as linear equations, linear physics. Schrodinger equation also the linear equation. But here is the first example you will discover what is called as a nonlinear equation. So what is I'm saying? V2 is given to you. That means W square plus W prime is given to you. And question I'm asking is, given W square plus W prime, tell me what is the corresponding W. Okay. So question is that unique? That's the question. And the answer to the question is no. Namely, not only a given W, but I have one continuous parameter family of W's, all of will give me same V2. How do I show this? Okay. So let us start with the given V2, which is W square plus W prime. And I claim that there is another W hat, call it, and W hat square plus W hat prime is also equal to W square plus W prime. Okay. So what does it give me? Suppose that therefore W hat is W of X plus another function phi of X. I don't know that function phi of X. W I know. Okay. And plug it in this equation. So as you can immediately see, W square, when you plug it in here and add here, W square will cancel it out. W prime will cancel it out. But you will get terms from phi square. Let's transfer sequence. And so you find then that they are not Oh, I think one before. Okay. So question is, what is the phi of x? Okay. Yeah. Next transparency, please. And you find that phi of, if I write down y equal to phi inverse, that is phi is equal to 1 by y, then one can show that y prime of x satisfies a first order equation, namely y prime of x is equal to 1 plus 2w of x times y prime. Remember, w of x is psi 0 prime by psi 0, y of x. Okay. And of course, y inverse of x by construction is nothing but phi of x, because you can solve this. This is what is called as the y prime is equal to 1 plus 2wx yx is what is called the Bernoulli equation. And its solution is already known for several hundred years. And therefore, from here, we know the solution for y inverse of x, which is phi of x. And that is equal to d dx of logarithm of I of x plus lambda, where lambda is a continuous parameter. It can take any value. I'll come to the restriction on lambda in a minute. And I of x is an indefinite integral of the ground state wave function of the initial potential with w of x. Okay. So we know initial w. So initially we know the corresponding ground state wave function, and we integrate that and just change the, call it x as x prime, and integrate dx prime, and upper limit x, lower limit minus infinity. That integral therefore only depends on x. So there, and it's an indefinite integral, because if you take the upper limit x to infinity, then of course it is equal to 1, because we assume the wave function to be normalized. But if it is just x, it's an indefinite integral. Okay. So therefore y which is phi of x therefore is d dx log of ix plus lambda. Now therefore w hat of x lambda, I have proved for you that given any w, the corresponding w, the corresponding given a potential v2, w is not unique, but there is a one continuous parameter family of w's, where w hat is equal to w of x plus d dx of log ix plus lambda. And I am going to show you that lambda can take any positive value, namely lambda can be greater than 0, and lambda can be any negative value less than -1. Next transparency, please. Okay. So what is v1 hat of x? Remember, v1 hat is w hat square minus w hat prime. Okay, and w we have just now seen that log of x. So therefore, we immediately find that v1 hat of x equal to v1 of x minus 2 d2 dx square log of I of x plus lambda. Okay, and the corresponding eigenfunction of the, in terms of hat psi 0 1 of x is lambda 0, and from here we can integrate and find out it is psi 0 1 of x divided by I of x plus lambda. Okay, so this is a normalized ground state wave function of hat potential if psi 0 1 is normalized. Now I want you to look at carefully at the denominator, I of x plus lambda. As we have seen, the I of x was the indefinite integral. Can you go one back step before? Yes. Now notice that I of, when I go, if x is equal to infinity, I of x is equal to 1. And when x is equal to minus infinity to minus infinity means 0. So Ix is equal to 0 if upper limit is minus infinity. It is equal to 1 if upper limit is plus infinity. Next transparency. So let us take the upper limit when I of x is equal to 1. So therefore this is equal to 1 plus lambda. So only thing I want is that this wave function should not be singular. So how will I ensure that? Since Ix is okay, if I can take lambda any value less than minus, since this is 1, if I can take lambda any value less than -1. No, sorry. If I take lambda any value greater than 0, okay, this therefore is always positive, no problem. Now next case, if x is minus infinity, this quantity is equal to, oh, I mean opposite, sorry. Yes. Okay. When upper limit is infinity, I of x is equal to 1. So if lambda is less than minus 1, therefore this quantity will be negative, but it will never vanish. So therefore this is non-singular. On the other hand, when x is equal to minus infinity, I of x is equal to 0. So long as lambda is anything value greater than 0, this can never vanish. So this will be non-singular. So just to avoid that singularity, we have omitted region from lambda equal to 0 to lambda equal to minus 1. Otherwise, lambda can take any value between this and that. Okay. And therefore, summarizing, what we have found is that given any potential V1, we can immediately construct a one parameter family of potential V1 hat, which are related to V1 by this formula. And now it is easy to see that all of the potential are same eigenvalues. Why? Because all these potentials V1 hat have the same partner potential V2. So therefore, since they have the same partner potential, so therefore all the potential was the same eigenvalues. Okay. So therefore, immediately follows that this we have constructed one continuous parameter family of potentials have the same eigenvalues as V1. And the construction is very easy. Why? Because this potential, we only unknown is I of x. And what is I of x? If I know the ground state wave function of V1, it's just semi-definite, this integral is I of x. So therefore, given ground state wave function of any potential, I can construct immediately from here one parameter family of potentials having the same eigenvalues as this original potential. Okay. Similarly, one can show, because same argument, because since they are same partner V2, hence the reflection coefficient and the transmission coefficient of all of them are the same partner. So therefore, all energy eigenvalues, reflection coefficient, transmission coefficient, all these potentials are different. However, the corresponding eigenfunctions are different. Why? Because you can see immediately here that psi01 of this hat family is different from psi01 because of this factor. And similarly, we can immediately use the supersymmetry. We can see how the psi11 will relate to psi11 hat relate with this and so on. So therefore, even the eigenfunctions are, so summarizing, given any potential V1 with one bound state, we can immediately construct one continuous parameter family of potentials having the same eigenvalues, same reflection coefficient, same transmission coefficient, but eigenfunctions are different. Okay. Nothing like example. Let's do the example. So next step, next transparency, please. So let's simplest example. One dimensional harmonic oscillator, W omega x by 2. And we assume x bar 2 equal to 1. So we can immediately construct V1, omega square x square by 4 minus omega by 2. And since we are subtracted, the ground state energy is n omega. Because half h bar is 1, so half omega, we are subtracted. And we know its ground state function, Gaussian. So immediately we can calculate its I of x. So I of x is 2 by square root by x to minus x to infinity e to the minus t square dt, where t is square root omega x by 2, So therefore, now that we know this I of x, we immediately know one continuous. So next transparency. Sorry, we go back. Okay, so we immediately know one continuous parameter family. Except, in fact, same spectrum n omega, all of them. And their eigenfunctions are broad. And for 1D oscillator, there is no scattering. So reflection, transmission, there is no question of scattering. So there is no question of reflection, transmission. And I had no time, so I didn't put figures here. But if you go by lecture notes there, I have also given figures for these potentials for lambda greater than 0 and lambda less than minus 1. And how these potentials sort of, shift from this thing. By the way, these potentials are very interesting because you can show that these potentials are not just arbitrary potential, but they have infinite number of conserved quantities. Namely, if we take the area under the curves for this potential, all potentials, they are always same, no matter what lambda is. You can prove that analytically. Next transparency, please. Okay. So this is probably my last topic. I want to show that unlike the WKB, which is exact for only the excited for the large quantum numbers, but inexact for ground state and lower quantum numbers, this new supersymmetry inspired WKB approximation by construction is exact not only for ground state, but also exact for large quantum number. Okay. So let me remind you, what do we do in WKB approximation? WKB approximation says that square root 2m e minus vx dx, and we take integral between the two turning points. What are turning points? Turning points where e is equal to v. And that we assume the potential such that it is equal to, we have 2 points, xl and xr. And those turning points, we take the integral, and that is equal to n plus of h bar. And these people have shown for several potentials, except for 1D oscillator is one example where this is exact. And there is another one most potential. Rest all other potential, it is not exact for ground state and first few excited states. Okay. So now what I want to do is, I want to start with the WKB approximation, but apply it for the supersymmetric partner potentials. Okay. So let me apply it for V1 of x. What is V1 of x? Recall V1, and now here I cannot put h bar equal to 1, remember, because WQ is nothing but h bar expansion. So I have to keep h bar. So I am keeping h bar and everything here. So remember, V1 of x is w square minus h bar by square root 2m w prime. So if you put minus here, this becomes minus and this becomes plus. Okay. So my WQB potential now in this for the partner potential V1 becomes, this is the case, is equal to plus. Okay. Now remember, w square of x has no h bar, formally at least, while w prime has no h bar, but there is h bar factor overall. And since WKB is an h bar expansion, what I do now is I expand this in the powers of h bar. So and write down as h bar to the power 0 term, then h bar correction, h bar square correction, h bar 3. In fact, this is exactly what one does in WQB approximation. People, by the way, for WQB approximation, not only have the WQB approximation to lowest order in h bar, then they have also developed it to h bar correction, h bar square correction, h bar 3 cube, etc., etc. So what I am going to do is now I expand in powers of h bar. So formally W is the order of h bar 0, W prime also is order of 0, but there is h bar here. And we expand left hand side in powers of h bar. Next. So what do we get here? In the lowest order we get e minus w square. And the first correction we get is h bar by 2 w prime x dx upon en1 minus w square, plus the higher order correction. And that is equal to n plus of h bar pi. That is a standard WKB. So I just doing standard WKB, and instead of the V, I am replaced with w square minus this h bar by 2 pi w prime. Now, and because of this xl and xr, since now we have got en minus or minus w square only, not w prime, so the turning point also will change from LR and L, L and right, left and right to A and B. Okay. And so this A, and the next term expansion we get this one, dot equal to n plus of h bar. Okay. Now what are the turning points? Turning points are what? Where en1 is equal to w square A is equal to w square B. That's the meaning of turning points, because where this vanishes. Okay. Now the remarkable thing, as you can notice here, if you put w of x is equal to t, w prime x dx is equal to dt. So you get simple integral dt upon e n1 minus t square. Now this integral is trivially done, is sign. So therefore we find that this first term in the correction is h bar by 2 sine inverse wx upon en1 square root from point A to B. Okay. But at the turning point w is equal to e1. So therefore, immediately find that this correction is equal to h bar by 2 pi. Okay. So in this way, you find that this correction is h bar pi by 2, which exactly cancel with this 0-point correction. And therefore, we find out to the first order in h bar, WK new approximation as applied to supersymmetric quantum mechanics gives me 2m en1 minus w square x is equal to n h bar pi n is equal to 0, 1, 2, 3. Now see the beauty. When n is equal to 0, you get 0. That means this immediately predicts that for ground state by construction, you will always find 0. Okay. On the other hand, by the way, if I had started with this supersymmetric WKB for the partner potential, can you go back one step, people? Yes. Instead of partners V1, if I start with V2, remember V2 is equal to W square plus W prime. So I would get minus W square, and instead of plus, I will get a minus sign. And because of this change of sign, next transparency. Now instead of plus sign, I will get a minus sign. That means this term will be equal to minus h bar pi by 2. So that minus h bar by 2 I can take it to this side, and I will get n plus 1 h bar pi. That means the lowest order SWKB condition for V2 I am going to get is n plus 1 h bar pi. But which is exactly the condition for the first excited state here for the V1. So therefore the fact that the relationship, well-known relationship between the partner potential energy eigenvalue is respected by the SWKB. So that is a very interesting point, that the lowest order SWKB approximation respect the supersymmetry relations. Next. Okay. And as we have seen, it is exact by construction for n equal to 0 and large n. And so one is hopeful that it will do better in between. Okay. Remarkably, and this is the remarkable point. So using this fact, for all shape invariant potential, people calculated a spectrum, exact spectrum, and not only for the ground state or the for n equal to infinity, the entire spectrum predicted by SWKB approximation for all shape invariant potential turns out to be exact spectrum. Now this is unheard of. WKB gives only for two potential exact spectrum, but here lowest order gives you exact spectrum for all shape invariant potential. This is the remarkable point. Okay. Next transparency, I don't know if there are nothing. Is it next nothing? Is it over? Okay. So if it is over, then maybe I would like to thank the first chairperson for giving me extra time so that I could finish the whole job thing. And I hope, of course, it is almost impossible in 1 hour for student to follow everything what I did, but at least I hope I have been able to convince you that supersymmetric quantum mechanics has a very rich structure, and once you follow this rich structure, you can construct several things. Let me know. Number one, given 1D of, for example, for infinite square well, we constructed one continuous parameter family of potentials, but now we know how to do it for any potential. Number two, we constructed reflectionless potentials. One parameter family of reflectionless potential starting from free particle. And number three, we discovered the so-called shape invariant potentials, which has the remarkable properties that all of them can be solved by one-dimensional oscillator like a dagger, just algebraically. And number four, we saw that given any potential is one bound state, if I know its eigenfunction, I can construct one continuous parameter family of potentials, all of which have the same aspect eigenvalues, reflection and transposition coefficient are all energy. And finally, we discussed the supersymmetric WKB approximation, because by construction is exact for all shape invariant potentials. So thank you very much. And I love the questions. Please, you are encouraged to ask the questions, please.
For giving such a nice lecture on the supersymmetry in quantum mechanics, particularly on the shape invariant potentials, giving such beautiful illustrations, and also extended to supersymmetry inspired WKB approximations. So I think all the participants must have been benefited out of this, but now they should interact actively with you. Let us have a discussion section for 5 minutes.
Yes. Okay. Yes, Prashant.
Yeah, ma'am, can I comment a couple of things? Just add a couple of things.
Yes, sir. Yes, sir.
I see. Just now, the method which Professor Khare used. This is for youngsters. There is a nature communication paper which exactly using isospectral deformation. One student who is now doing his Ph.D. in Pittsburgh from ISO Kolkata, Nitish Chandra, he has a nature communication paper showing that in fact the band gap can be suitably modified in photonic band gap materials. Exactly same example which Professor Khare dealt with. So these methods have really found use in technology, and there is a science paper earlier some time back which also showed how to use supersymmetry to reduce noise. So they have designed better potentials. So these techniques are actually useful, possibly in quantum computation soon. And one more comment I would like to add, that when computer was found out to be useful for physics, Fermi started with Fermi-Pascal model, which is about how equilibrium arises in statistical mechanics. That led to KDB equation, integrability, and isospectral deformation, as Professor Khare has mentioned. So now that we have quantum computer, possibly something new will come out, just like Professor Khare has used. So these methods are very useful. It is up to our imagination how we take it forward. Thank you.
Probably two questions.
Yes, please.
Thank you for a very interesting and.
Can I see your face, please, Ranjit?
Yes, sure.
Yes.
So, thank you for a very interesting and informative talk.
Yes.
Probably two questions. The first one is, did you consider dissipation mixed state in your calculations? This is the first question, because you consider pure state.
Okay. To answer question, I didn't have time to discuss those things here. For example, there are potentials, okay, which are called PT symmetric potentials, where actually you find which are complex potentials, but PT symmetric potentials. And in those potentials, exactly what you said, that namely, depending on which, in one direction, if you find that there is a dissipation, other find is the opposite of dissipation. Okay, and there are some supersymmetry inspired potentials which are also people have found out very novel properties, the reflection coefficients, transmission coefficient, and very interesting property they have found out. So indeed this has been considered. Your second question, please.
Probably this is a repetition of the comments I mean from Professor Panigrahi. What kind of benefits or new physics interpretations do you see in using supersymmetry in problems of quantum technologies?
Well, I'm not sure I have much, but Professor Panigrahi is really expert in this area, and he knows much more than me about this application and quantum computation and all this application, etc. So he has already amplified. So I don't want to add anything more than what Professor Panigrahi already has said. Maybe Professor Panigrahi wants to add something more.
No. There are only point is that people have used it for modifying potentials. People have used it for noise reduction, and in real lattice, optical lattice particularly, people have actually realized supersymmetric patterns. So those things, it's exactly in quantum computing how it will be useful, I cannot say right now. But optical lattice and realistic systems, people have actually used these techniques.
Thank you. That's it from my side. So, thank you very much.